The study of the universe spans almost inconceivable extremes of size and distance and time. From the vast island of stars we call a galaxy, to the tiny atom and the particles that comprise it. From cosmic events that occurred billions of years in the past, to microcosmic events in the present that endure for only billionths of a second. To explore the universe at these extremes, the scientist builds instruments that extend his reach and his vision. His great telescopic eye has the light-gathering power of 1,000,000 human eyes. It peers not only into the depths of space, but far back in time, since the light it now observes may have left its source when dinosaurs inhabited the Earth. His telescopic ear is tuned to the invisible radio sky. It detects not objects, but the radio regions associated with them, and at distances far beyond the range of the largest optical telescope. But the radio waves and the visible light that pass through the Earth's atmosphere to these ground-based telescopes are only part of a broad spectrum of radiation, most of which is blocked by the atmosphere. So electronic instruments are lifted above this murky and turbulent layer. Airborne by rockets, by balloons, in unmanned astronomical observatories, in manned laboratories, and in spacecraft orbiting the planets. Instruments probe the near and distant environments of space and open new windows on the universe. In the beginning, it is believed, all the matter of the universe was contained in a primordial atom, an unimaginable concentration of elementary particles. In one gigantic detonation, the contents of this cosmic fireball were hurled outward in all directions. After 1,000,000 years of expansion, the universe was an intense blaze of light. Then the radiation cooled, and after hundreds of millions of years, great clouds of hydrogen gas began contracting, and in time, evolved into the galaxies we now observe. Inside these galactic whirlpools, smaller fields of gravity condense hydrogen into stars. Stars are inconceivably hot. So hot, they sustain thermonuclear reactions that transform hydrogen into heavier elements. Sometimes their hydrogen fuel burns so fast, they flare out in violent explosions, hurling new elements across space. Like a great wind, the radiant energy of starlight drives these clouds of dust and gas throughout the galaxy. Out of these clouds evolve new generations of stars. More than half the stars in our galaxy travel in groups of 2 or more, orbiting around a common center of gravity. Like galactic comets, Immense clusters of stars swing in and out of the galaxy in vast, eccentric paths. Some small stars do not travel in the company of other stars. Our own sun is one of these. To the astronomer, the sun is a vast laboratory for the detailed study of a star's structure and energy. The vertical tower of the solar observatory supports a heliostat mirror which tracks the sun, gathers its rays, and reflects them down a light shaft that extends 300 feet below ground. At the end of the shaft, the rays are cast back to an observing room where minute-by-minute changes across the face of the sun are observed. Another mirror projects a light beam to a spectroscope, an instrument which splits the light into its component colors, a visible spectrum. The dark lines that cut across the spectrum band are produced by the radiation from the sun's interior shining through its atmosphere. Each line is the signature of a chemical element such as sodium, iron, calcium. It is this array of lines that forms the code which describes the properties and motion of a star. By narrowing the view of the sun to a single line of the spectrum, each level of the solar atmosphere can be photographed, and each reveals a remarkably different aspect. And with the addition of computer mapping and color processing that distinguishes levels of brightness, a detailed and multidimensional picture is obtained of a sun undergoing dramatic and turbulent change. The sun is a sphere of hot, seething gases and surges of radiation. Most of the light we get from the sun comes from the thin, bright layer which defines its visible edge, the photosphere. Above it, the chromosphere, a region of flaming outbursts of gas, extends through a transition zone to the thin outer atmosphere of the corona. Once thought to be a quiet layer of the solar atmosphere, the corona is now revealed to be a region of dramatic large-scale changes and unexpected turbulence, with temperatures reaching millions of degrees. Deep beneath the sun's atmospheric shell is the core, a violent nuclear furnace. Here, hydrogen is fused into helium, and in the process, some of the matter is converted into an enormous amount of energy. Radiating outward as a gas, it convects like a boiling liquid beneath the surface. The turbulent, bubbling motion is visible in the granular cells of the photosphere. Sunspots, regions of intense magnetic fields, appear on the surface, disappear in a few hours, or grow and persist for months in a mysterious 11-year cycle. The sun rotates once in 27 days. Because its equatorial regions rotate faster than the polar caps, the shearing action in the gas contorts the magnetic field into tangled structures which give rise to the sun's eruptive action. Shaped by these magnetic fields are the spectacular prominences, titanic streamers of gas reaching heights of more than 500,000 miles above the surface. The greatest explosions in the solar system are flares, intense bursts of light erupting with the force of billions of hydrogen bombs. They move at hundreds of miles a second. Then, after minutes or hours, they fade away. The dark areas across the solar disk are coronal holes, which may provide new clues to the sun's interior, and may be a source of the solar wind that blows outward to the farthest planets. On Earth, effects of these solar events are visible when auroras light up the dark Arctic sky and radio communication is disrupted. The Sun is an average, middle-aged star. Yet it will generate heat and light for billions of years to come, as it has for 5 billion years past. It dominates the motions of all bodies in the solar system. Nearest the Sun and obscured by its intense glare is Mercury, a cratered planet much like our moon. Temperatures rise to 800 degrees, but no clouds or atmosphere protect its ancient surface from the searing heat. Moving outward from Mercury, we encounter Venus. Its perpetual cloud cover traps the radiant energy of the Sun within an atmosphere of incredible pressures. From the surface, only a reddish glow reveals the presence of the Sun. Beyond Venus, 93 million miles from the Sun, is Earth. Its great oceans forming the clouds and air currents which warm and irrigate the planet, shape its continents, and nourish life. Its satellite, the Moon, airless, waterless, and scarred by meteors that have bombarded it since the time of its formation, now bears the imprints of our astronauts. A probe of the planet Mars has discovered a dynamic and evolving planet with unexpected geological features. A volcanic mountain, many times larger than the largest volcano on Earth. A vast and deep canyon extending for 2,500 miles. And dry, river-like channels that may have been carved by running water. Beyond the orbit of Mars is the belt of asteroids, craggy chunks of rock and metal, some as small as boulders, others hundreds of miles in diameter. About 500 million miles from the Sun, we encounter the first of the giant gas planets, Jupiter, the colossus of the solar system. More massive than all the other planets combined. Deep beneath the maelstrom of clouds that band its surface is a primordial atmosphere much like that in which life awakened on Earth millions of years ago. And drifting on its surface is the mysterious red spot, an immense cyclonic storm that has raged for hundreds of years and continues unabated. Radiating more energy than it receives from the Sun, and circled by 14 moons, Jupiter is like a miniature solar system. The next largest of the gas planets is Saturn, girded by rings which, as we approach them, resolve into countless particles of frozen debris and ice, each a tiny moon orbiting the massive planet. And as we continue past the frozen worlds of Uranus and Neptune, we arrive at the outermost planet in the solar system, Pluto. It moves in a dim twilight of unimaginable cold. The Sun, 4 billion miles away, is only a brilliant light in the night sky. To travel beyond the solar system to the nearest star would require a journey of more than 5 trillion miles. Yet our sun is only one of 100 billion stars, widely separated from one another in time and space, but all bound by gravity, and all revolving around the central core of our galaxy, the Milky Way. Drifting between the stars are vast clouds of gas and dust, the nebulae, made luminous by the radiation of stars within or near them, or darkly obscuring the light of whatever lies behind them. Here, new stars are being born. About a half-century ago, our galaxy was thought to be alone in the universe. We now know it to be one of a local group of about 20 galaxies. And strewn through the vast reaches of space are more than 10 billion galaxies, grouped in clusters as far as our most sensitive instruments can reach. Little is known about the evolution of galaxies, and why some are formless or irregular, others elliptical, and still others spiral-shaped. And we know as little about the galactic core and its role in the galaxy's evolution and structure. The problem has become more perplexing by the discovery that some galaxies are in a state of extreme disarray, exploding, ejecting gaseous matter, or interacting with other galaxies. Even more puzzling are quasars, star-like objects, emitting as much energy every second as the sun radiates in some 10 million years. They appear to be among the most remote objects in space. Stars are born, live out their lifespans, and die. The life history of a star is marked by an opposition of two kinds of pressure. One is the pressure created by the energy in the core of the star, pushing the surface outward. The other is the crushing force of gravity pulling the star's surface inward. When these are balanced, a star becomes stable and shines steadily. As hydrogen fuel is depleted, the release of energy is insufficient to withstand the gravitational pressure, and the core collapses. But compression by gravity raises the temperature in the core, and helium ash rekindles the nuclear fires. Vast amounts of energy are released and lift the outer zones against the force of gravity. The star is now a red giant. In the final stage of its evolution, it is the mass of a star that determines its fate. The Sun, a medium-sized star, remains stable for approximately 10 billion years. Then it will expand to 400 times its present diameter. As it expands, it will engulf the inner planets, Mercury, Venus, Earth, and Mars, and create a nebula extending past the outer planets. After millions of years, its reserves of nuclear fuel will be exhausted, its outer layers will have dissipated, and only a white dwarf star remains, no larger than the Earth. Slowly cooling to zero temperature, it will end its life as a black stellar corpse. When a star more massive than the Sun reaches the red giant stage, the collapse of its core raises its temperature billions of degrees and triggers a spectacular detonation. A supernova explosion. At the center of the explosion, a residue of the star is crushed by gravity to a neutron core, only a few miles across, but so dense that 10 billion tons of its matter would fill only a tablespoon. It spins rapidly, generating radio signals in its strong magnetic field. And a radiation beam sweeping past the Earth is observed as a pulse. The star is known as a pulsar. An even stranger end is predicted for very massive stars. According to the laws of gravity as presently understood, nothing can stop its collapse. The star disappears from our universe, leaving a black hole in space. Its presence can be deduced only by its influence on a visible companion star, distorted out of shape by the black hole's gravitational attraction. Gas, pulled off the visible star, circulates about the black hole, and in the dizzying plunge, it emits X-rays which can be detected in space. No light or matter can ever leave the intense gravitational field of this cosmic abyss. The physical laws that govern the conditions within this bizarre object are totally unknown to us. The evolving universe itself must come to an end. If it continues to expand indefinitely, the light of every star will in time be extinguished, and the galaxies will disappear into infinite darkness. But if gravity halts the expansion, the universe will fall back on itself. Galaxies will lose their separate identities. Stars will explode, and the sky will again be ablaze with light. Finally, all matter will be engulfed in a fireball like that from which it emerged. All things on Earth, living and inert, are formed from the elements forged in some distant and unknown star. On Earth, atoms joined together in definite numbers and patterns compose the organic molecules which form living cells. Since the discovery of complex molecules in the chill vacuum of interstellar space, there is reason to believe that among the countless galaxies in the universe, there are stars orbited by planets favorable for the evolution of intelligent life. Is space travel to these planets possible? Time and distance may be insurmountable barriers. The spacecraft Pioneer, now speeding toward the outer planets and beyond, traveling at 35,000 miles an hour, would take almost 80,000 years to reach the nearest star, Alpha Centauri. A spacecraft traveling 2,500 times faster than Pioneer, at 10% the speed of light, would require so great an expenditure of energy that until new sources have been tapped, it must remain an invention of science fiction. A more practical strategy in the search for extraterrestrial life is to tune in on radio signals traveling at the speed of light, beamed perhaps by creatures on the planet of some distant star. Someday, an array of telescopes, earthbound or lifted to the far side of the moon, may hear faint but unmistakably meaningful sounds amidst the din of cosmic radio chatter. That moment will signal a change in the human condition that we cannot foresee or imagine. For man, wrote H.G. Wells, There is no rest and no ending. He must go on, conquest beyond conquest. And when he has conquered all the deeps of space and all the mysteries of time, still he will be beginning.